Hello and welcome to this lesson, where we'll learn about resource reservations and kube-reserved resource optimization in AKS. During this lecture, we'll learn about and cover resource reservations constraints, followed by how the reserved CPU works. Then, we'll look into how reserved memory works for Kubernetes versions 1.28 and lower. After this, we'll learn how the reserved memory works for Kubernetes versions 1.29 and higher. Starting with Kubernetes version 1.29, a behavioral change was introduced with the purpose of optimizing the reserved memory, and this is called kube-reserved optimization. At the end, we'll discuss some of the confusions these resource reservations can lead to. Okay, let's start by understanding the goal of the resource reservation in AKS. AKS reserves resources from the nodes to ensure proper functionality and to avoid competing for resources between pods, system daemons like kubelet and containerd, and nodes operating system. A consequence of this is the fact that the total resources on your node and the resources that are really allocatable in AKS differ as a result of this usage. We can describe the node to find the node's total capacity and allocatable resources by looking under the capacity and allocatable fields. The compute needs of your application are mostly related to CPU and memory. Before deciding about scaling your AKS cluster or setting limits and requests, we need to understand what AKS resources are needed to ensure the proper functionality of the nodes. Limits are the maximum amount of resources that can be used, and requests are the minimum guaranteed amount that is being reserved for the container. For a node, the limits can be overcommitted, which means over 100%, but resources cannot be more than 100%. Requests are relevant for scheduling decisions, and it is important for you to be aware of them. In case you are wondering, based on how the resource reservation is calculated, I would like to mention that it depends on multiple factors, but the most relevant is the node size. You will understand better once we look into this in more details. The resource reservation is set at kubelet level using the kube-reserved parameter. Before understanding how the CPU and memory are calculated, let's explore a little the describe of the node and the kube-reserved parameter. First, I will generate a list with my nodes, and further I prepared the kubectl describe node command, which will show us details about the total CPU and memory capacity as well as the allocatable CPU and memory capacity plus other relevant details. First of all, I'll check for CPU. It generated for all the nodes, but let's take the first one as an example. And we can see that for the CPU, the total capacity is different from the allocatable one. And if I generate for the memory as well, here we also conclude that allocatable is different from the total capacity. And as we discussed, this is set at kubelet level via the kube-reserved parameter. So if I take one of the nodes, let's take this one, for example, I replace the name here. But first of all, I'll run a kubectl proxy command because we'll curl localhost in order to generate the configuration of the kubelet. I'll open a new tab here for the terminal and execute the curl command. Okay. And we can find that for this node, which is node pool 129A, we have kube-reserved, and it says that it reserves 100 millicores for the CPU and 1792 megabytes for the memory. Note that this is MI, not MB, and MI means megabyte, while MB means megabyte. I'll explain you the difference in a moment. If I copy this, let me take it from here and put it here. Okay, so this is for the node with 129A. I'll get back here. And for the node with 129A, we have this, which means around 7 gigabytes minus, let's say 1.8 gigabytes. We are approximating. It would result into this. If we also look into the CPU, so it reserves 100 millicores. We can see that the total capacity is 2 CPUs minus 100 millicores, which means 0.1 cores. It would result in 1900 millicores. Okay, let me delete this from here. And I'll resume to our presentation. Let's understand how the CPU is reserved. As you can see on the screen, it depends on the number of cores on the host as per the following table. For example, if the node has 2 cores, 100 millicores will be reserved by AKS. We have already concluded that, but let's take a second look. So, for all the nodes, we can see that they all have 2 CPUs for the capacity, okay? However, if we check allocatable, all of them have 1.9 CPU or 1900 millicores. The CPU reservation is not relevant to the Kubernetes version. It is the same for all the Kubernetes versions. Further, let's discuss the reserved memory for Kubernetes versions 1.28 and lower. The memory reservation, regardless of the Kubernetes version, is the sum of 2 values. The first one is the kubelet daemon, which is by default installed on all AKS nodes to manage container creation and termination. In Kubernetes versions 1.28 and lower, a node must have at least 750 MB allocatable by default on AKS due to the kubelet daemon's memory available 750 MB eviction rule. A running pod will be terminated by the kubelet in order to free up memory on the host machine when host falls below that threshold for available memory. Then, the second aspect is the regressive rate, which is needed for the kubelet daemon to run effectively, and it is calculated as per the table on the right side. If the node is a Windows one, 2 more gigabytes are reserved for system processes. It is important to understand that these resource reservations cannot be changed and they are calculated as mentioned above. We already checked the CPU for one of our nodes. Let's calculate with respect to memory as well. I'll clear the screen. Okay, let me turn off kubectl proxy. Clear. And if we look around, all our nodes are using standard DS2 v2, which include 2 vCPU and 7 GB of memory. Here, I explained the difference between gigabyte and GB. As we can see, gigabyte is a traditional metric style of measurement with 1 GB equaling 1000 at the third power bytes, while GB represents the binary method of measuring data at 1024 at third power bytes. Here we can see the difference between gigabyte and GB. Also here is the difference in pronunciation between other measurement units. Okay, and these are the nodes. This is how they are configured. The name here is different because this one is its 1.29 Kubernetes version and it has 110 pods. This one is also with 1.29 Kubernetes version and it has 15 pods. And this is 1.28 version, the only one with 1.28 version, and it has 110 pods. As you can see, the difference between them is at Kubernetes version and number of pods. You will understand why this is relevant a little bit later. Okay, so coming back to what I prepared here, I run a kget node. This is our node with Kubernetes version 1.28.5. And this is how we calculate the reserved memory. So 25% of 4 GB plus 20% of 3 GB plus 700 MB, which is the eviction threshold, it will result into this, which in the end will mean approximately 2.35 GB reserved. I put approximatively because some values are with gigabytes while the others are with GB. So also if we check the documentation or if we describe one of the nodes, so for example kubectl describe node, and let me take this node. Okay, I'll scroll up. We can find out that the values are here in KB, which is the equivalent of GB. But if we check the official Microsoft documentation, here for resource reservation, some values are with megabyte. Also, if we check the size here is with GB. So just to let you know that there is a difference between them, but I performed the math approximatively. I didn't take into consideration too much this difference because my goal is to help you understand how it works, not to teach you how to calculate based on the fact that if this is GB or gigabyte and stuff like that. So basically I just want you to understand the main idea of how the reserved CPU and memory works. Okay. So coming back to this, our conclusion is that 2.35 gigabytes of memory are reserved. And we know that the total capacity of our node is 7 gigabytes. And if we do the math, it will result that 4.65 are allocatable. And if we check our node, we can see that for real, if you convert this to gigabytes, it will result in about 4.65. And this is how it works in 1.28. In 1.29, this is different, and we'll understand that in a little. Further, let's discuss kube-reserved optimization. As mentioned a little bit earlier, this is a behavioral change introduced for Kubernetes versions 1.29 and higher, meant to optimize the memory reservation in order to allow users to utilize more memory while AKS reserves less memory than before. The total reserved memory is the sum of the kubelet daemon eviction threshold plus a rate of memory reservation. For Kubernetes version 1.29 and higher, the kubelet daemon requires at least 100 MB allocatable at all times, compared with 1.28 and lower when it needed at least 700 MB. The rate of memory reservation is the lesser value of one of the following: 20 MB multiplied by the max pods value plus 50 MB or 25% of the total system memory resources. If the node is a Windows one, 2 more gigabytes are reserved for system processes. Let's look at some examples to better understand how it works. I'll clear the screen. I'll scroll down. Let me run a kget node so we see again our nodes on the screen. Okay, let's have all the data on the screen. And as we discussed, we have two nodes with Kubernetes version 1.29, where the way on how the memory is reserved is different comparing with 1.28. So let's take first this node 129A. This node has 110 pods. And in order to calculate the reserved memory, we know that we have to calculate two things. First of all, we need to calculate based on the number of pods. So 20 megabytes multiplied with 110 pods plus 50 plus 100, it will be equal to approximately 2.35 gigabytes, or 25% of the total memory, which is 7 gigabytes plus 100 megabytes. In total, it will be approximately 1.85 gigabytes, and 1.85 gigabytes is lower than 2.35 gigabytes. So this is the reserved memory. If we decrease 1.85 from 7, it would mean that approximately 5.15 gigabytes are allocatable. And let's describe this node to confirm. So I'll run a kdescribe node, the name of the node. And what we care about is the allocatable memory. Okay. And as expected, this is around 5.15 gigabytes allocatable. Let's now check for the next node, which is this one. If we describe this, okay, describe node. Let me copy the name. This one has 15 pods. So if we check here, 15 pods. And again, we have to understand which is the lower value. First of all, we have 20 megabytes multiplied with the number of pods, which is 15 plus 50 plus 100 megabytes. It will result in a total of 0.45 gigabytes. The other option is 25% of the total capacity for the memory plus 100 megabytes, resulting in approximately 1.85 gigabytes. And obviously 0.45 is the lower value. If we decrease 0.45 from 7, it will result in approximately 6.55 gigabytes allocatable. And if we check here for allocatable, this is approximately the value that we have. As mentioned, there is a little bit of a difference because there is a difference between gigabyte and GB that I didn't fully take into consideration. But if we would convert all the values, it would result in exactly the allocatable value that is written here. Okay, now that we have a better understanding of resource reservations in AKS, Let's think of what confusions this subject can lead to. One of them is the fact that you can think that the AKS nodes cannot use their real capacity. It is obvious that this would be unexpected behavior caused by the fact that AKS reserves some of the CPU and memory. Another confusion that can appear is the situation when you create a pod with some requests and it gets stuck in pending. For example, you create a node pool with nodes that have 8 GB of memory each, and you create a pod with 7 GB requests that get pending. If AKS reserved at least 1 GB, it is expected that you won't have 7 GB of memory for that pod and it will get in pending state, so you can consider using lower requests or a SKU size with more memory. Based on the above idea, there may be the situation in which the cluster autoscaler or HPA are not able to add new nodes or pods if the requests are higher than the allocatable resources. I hope this provides more clarity about resource reservations in AKS and that you can use this as a foundation when making a scheduling or scaling decision. I hope you found this lesson useful. If you enjoyed this content and found it valuable, feel free to watch the other videos on the screen, and please don't forget to hit the like button, subscribe to the channel, and ring the notification bell to stay updated. Your support means a lot to me, and I cannot wait to bring you more insightful content. Until next time, take care and happy learning!